Alright, thanks for watching. And today I will calculate an incredible integral. Namely, I'll calculate the integral of sine of x to the n dx from 0 to infinity. Because in another video I did this integral of sine of x squared, but now we have this nice generalization to the case where n is greater or equal to 2. And also, in this other video, I presented a way of doing it with contour integration, which you could also do here, but the cool thing is the method I present today doesn't involve any contour integration. It's just a straightforward method with some special functions. And I want to say it doesn't really involve complex analysis. It just involves it does involve complex numbers, but it just involves some calculus, which is really neat. And by the way, this is not my idea. I would like to thank Sanchu Lee on Mass Stack Exchange who came up with this idea. Really, really cool. So, what is the first step? Instead of dealing with sine, let's deal with complex exponentials. So, calculate the integral from 0 to infinity of ei x to the n dx, which if you like is the integral from 0 to infinity of cosine x to the n plus I sine x to the n dx. And what is then our answer? Our answer will just be the imaginary part of this. So whatever answer we find, just take the imaginary part. E of I x to the n. Alright, that was the first thing, and really now the very first step. So that was like step 0. Now step 1. Now, and this crucially uses the fact that n is greater or equal to 2. Because out of this, it turns out, let's make this integral a little bit more complicated. Dx. Okay. Instead of using n, let's use 1 over n. Because that guarantees that that number is between 0 and 1. So write n to be 1 over alpha. Then alpha is 1 over n, and alpha is between 0 and 1. And let's define the following more complicated integral. I of alpha is the integral from 0 to infinity of ei x to the 1 over alpha dx. And because you see x to the 1 over alpha, let's use a nice u sub. So let u be x to the 1 over alpha, and it turns out du, we can write this purely in terms of u, because du then just becomes 1 over alpha, x to the 1 over alpha minus 1, and if you want, that becomes 1 over alpha, x to the 1 over alpha over x, again dx, but x to the 1 over alpha, that's u, so 1 over alpha u, and then x is just u to the alpha, so if you do 1 over x, it's u to the minus, it's u to the minus alpha dx, and that becomes 1 over alpha u of 1 minus alpha dx. And this is du. So to get dx, it's alpha u to the alpha minus 1 du. In other words, your integral becomes slightly simplified. So what we're left with is simply that our integral is as follows. So I of alpha equals, 0 to the 1 over alpha, that's just 0. And again, alpha is a positive real number. So it's 0, and then infinity to the 1 over alpha is infinity. And then we have eiu and then our term alpha u to the alpha minus 1 du, which we can just write as alpha integral from 0 to infinity u to the alpha minus 1 e to the iu du. So that concludes step 1. So step 2 is to use something kind of interesting. This is already a complicated integral. Let's make it even more complicated. It's strange because you don't usually use math to simplify things, but here we make stuff so complicated that it becomes easier. So this integral is an integral from alpha times integral from 0 to infinity. Instead of using u, let's use x again. So x to the alpha minus 1 eix dx. And notice this term doesn't really converge very well, but let's make it converge by adding a little term here. Maybe not convergence, but you'll see it'll make stuff more interesting. So it turns out this is true, that this is equal to the limit as epsilon goes to 0 of alpha integral from 0 to infinity x to the alpha minus 1 eix, and let's add an e to the minus epsilon x dx. Because for epsilon positive, this goes to 0, so kind of this makes it converge. And why can we do this? It actually relies on something called Abel's theorem. Which says the following. So here's a sum version, is probably an integral version, and it says, suppose that the series converges. And you have a series that has radius of convergence 1. Has radius of convergence. Then it says, of course, the series converges at 0 and then also converges at 1. But what's more interesting is, if you let x goes to 1 from the left, then it's still continuous. Then if you want this series, x to the n, let's call it p of x, is continuous at x equals 1 from the left. And this is kind of the analog of this, because we're kind of saying, because this term is ex I minus epsilon, and we're kind of saying this is continuous to continuous at I, but from the left. So it's some generalization of this, and then again, I'm not going to prove this, but heuristically this is why it's true, because also technically you can't really use dominated convergence because this function is not integrable. But so assume this is true, and you'll see in a second why it's so useful. Then we want to study this term, and for this let's introduce some special functions. As I said, no contour integration here, but we have to use something else. In this case, let's use the gamma function. As it turns out, the answer relies on the gamma function. So step 3. And I use it in this way. Notice that gamma of 1 minus alpha can be written as the integral from 0 to infinity of t of minus alpha e of minus t dt. Where in general, the gamma function, let's say at k, is just the integral from 0 to infinity tk minus 1 e of minus t dt. So in fact, with k is 1 minus alpha, you get precisely that. And we'll use this to get a nice identity of gamma of 1 minus alpha. For this, let's use the following u substitution. So t equals to xu, and I think here u is the variable, so this is fixed. Some fixed constant, because basically here we're integrating with respect to x. And so what we want to do, we want to define u to be t over x. And with this u sub, let's see what we get. Then, if t is 0, u is 0. And if t is infinity, assuming x is finite, which for each step is true in the integral, we get infinity. And then t is just xu, and then minus alpha. And then e of minus xu. And lastly, what is dt? Or I guess what is du? It's 1 over x dt. And so a dt is x du. So we're left with x du. Which we can simplify. Notice x comes out of the integral. X to the minus alpha comes out of the integral. So we're left with x to the 1 minus alpha. Integral from 0 to infinity. U to the minus alpha. E of minus xu du. And in particular, we have a nice identity of x to the 1 minus alpha, or I guess x to the alpha minus 1 in terms of the gamma function. And the reason we're using this is because this integral involves x to the alpha minus 1. So what do we get? We get, again, gamma of 1 minus alpha. It's x to the 1 minus alpha times this weird integral, 0 to infinity, u of minus alpha, e of minus xu du. And so, if you divide by this and divide by this, you eventually get x to the alpha minus 1 equals to this weird integral, xu du, over the gamma function. In other words, this is so interesting. Let's take this simple term, x to the alpha minus 1, and make it even more complicated. And plug it into the even more complicated expression of our integral, which leads us to step 4. So what is I of alpha? Well, there is a limit as epsilon goes to 0 of alpha times the integral from 0 to infinity of, remember this term was x to the alpha minus 1. Let's replace it with this integral. Integral from 0 to infinity, u to the minus alpha, e of minus xu du, over that gamma function. And for the other term, we have like an eix, e to the minus epsilon x. And let's write this as e to the minus epsilon minus I x, and then dx. Okay. All right, so we have this. So as I said, let's make the in French, you always say, pourquoi faire simple si on peut faire compliqué? Like, why make things simple if we can make them complicated? But it turns out it'll be so complicated that it'll work. And you might also ask, why did we do a double integral? So let's do limit epsilon goes to 0 of alpha over gamma of 1 minus alpha, integral from 0 to infinity, integral from 0 to infinity of u to the minus alpha, e of minus xu, e of minus epsilon minus ix, du dx if you want. And guess what? We have a double integral. What time is it? It's Fubini time. So assume you can interchange the two. Which, by the way, let me now explain why this epsilon is important. If there wasn't this epsilon, as I said, the integral might not converge. but it's precisely because it's epsilon that we kind of have exponential decay, and this actually is the thing that allows us to interchange the integral. So what we're left with is limit epsilon goes to 0 of alpha over gamma, 1 minus alpha. Let's interchange the two, which is not too bad. And u to the minus alpha, and then e of minus xu, e of minus epsilon minus ix, dx du. And notice a lot of the terms go outside. I mean, I guess one, which in this case is a lot. So we're left with limit epsilon goes to 0 of integral from 0 of this term there, alpha over gamma of 1 minus alpha, integral from 0 to infinity, u of minus alpha, integral from 0 to infinity of a very nice term, so e of minus u plus epsilon minus I, x, and then this is dx, and then du. But you see, that whole thing with respect to u was hard to calculate, but this term is actually easy to calculate with respect to x. Because this one, an antiderivative, is simply e of minus u plus epsilon minus I x over minus u plus epsilon minus I. And that's from x equals 0 to x equals infinity. And again, I want to emphasize, if we didn't have this epsilon, we wouldn't really know what this whole thing converges to. But because of this epsilon, the modulus of this is at most like e of minus epsilon infinity. So this term, because it decays exponentially, this whole thing goes to 0. And what we're left with is just a term at 0, which now becomes e of 0, which is 1, and then u plus epsilon minus I. And therefore, a complicated integral is then just the following. We still have the limit as epsilon goes to 0. That was like the climax of it all. And now, because we simplify this integral, it'll just be simpler and simpler and simpler. So we have limit epsilon goes to 0, again alpha over gamma, 1 minus alpha, integral from 0 to infinity, u of minus alpha over this term, u plus epsilon minus I du. And now it's safe, it's like safe to remove the USB drive, safe to let epsilon go to 0, and we have alpha over gamma, 1 minus alpha, integral from 0 to infinity, u of minus alpha, u minus I du. Still too complicated, but we'll simplify this. We can write this in terms of known functions. So we get alpha over gamma, 1 minus alpha, and I guess this is step 5. So I want to say, let's say we're like 2/3 done. So not almost done, but close. So step 5. So what we have, I alpha is equal to this term, and just to simplify matters, let's multiply both sides by the conjugate form, u plus I and u plus I du, and then what you're left with is alpha over gamma of 1 minus alpha, integral from 0 to infinity, u of minus alpha, u plus I, and then u minus I times u plus I, that's u squared plus 1. So minus I squared, which is minus minus 1, which is plus 1. du, which you can really separate in terms of two integrals, alpha of gamma of 1 minus alpha, integral from 0 to infinity, u of, if you want, u times u of minus alpha, so u of 1 minus alpha over u squared plus 1, and then plus I times u of minus alpha over u squared plus 1 du. And again, those are still complicated integrals, but we can just simplify. So here's the next step. So, as I said, we would like to write this in terms of a known function. So let's study the first term, u of 1 minus alpha over u squared plus 1 du. Now, it would be nice if this u squared were just like an x or a t, because we want to use, as I said, an unknown special function. And for this, let's just use the u sub, t be u squared, then dt, it's 2u du. In other words, u is square root of t, or I guess t is u squared, and then we get integral from 0 to infinity of, again, t is square root of u, so we get t, so u is square root of t, and therefore we get t to the 1/2 to the 1 minus alpha, and then dt is 2u du, so we get 2 square root of, du is 1 over 2 dt, du is 1 over 2u dt, which is 1 over 2 t to the 1/2 dt, and then 1 plus t. And if you simplify this, this becomes t to the 1/2 minus alpha over 2, and then minus 1/2, and that simplifies. So in the end, the numerator is just t to the minus alpha over 2. And we're left with 1/2 integral from 0 to infinity, t to the minus alpha over 2 of 1 plus t dt. And we can write this in terms of strange form. So integral from 0 to infinity of t to the, let's write it as like the gamma function. Let's write it to something minus 1. So it becomes 1 minus alpha over 2 minus 1. And 1 plus t. The same thing here. So 1 minus alpha over 2 plus alpha over 2. So if we let this to be a and let this to be b, then this becomes precisely of the form integral from 0 to infinity t to the a minus 1 over 1 plus t to the a plus b dt. And this is precisely one of the forms of what's called the beta function. So this is BAB. Almost like BAB, but BAB. Okay, so that's 1/2 of BAB. And that's actually one, B was just, notice B is 1 minus A here. So it's 1/2 B of A of 1 minus A. And the nice thing is there's this beautiful identity with the beta function, which I'm sure I did in one of the other videos, that, which I think it just follows from Euler's reflection formula, but this thing is just pi over sine of pi A. So we get 1/2 pi over sine of pi A. Paella, okay. And I don't know what's up with me today. But by the way, so I think alpha was strictly between 0 and 1. So this thing, it's never an integer. So we don't have to worry about sine of pi A being 0. All right, but now let's simplify this further. So this is pi over sine of pi of 1 minus alpha over 2. And then that's 1 over 2 pi sine of pi minus pi alpha is alpha pi over 2. And remember, sine of pi minus something, it's minus sine, so sine of pi minus y, it's minus sine of minus y using the the addition formula for sines, and that's just sine of y. So really, what we're left with is pi over 2 divided by sine of alpha pi over 2. And that was our first integral. Now, so that was, if you want, integral from 0 to infinity, u of 1 minus alpha over u squared plus 1 du. Which is great, a completely explicit form. And similarly, I think if you just follow the exact same steps, you get integral from 0 to infinity, u of minus alpha of u squared plus 1. It's the same thing but with cosine. All right, and that's good because, by the way, we have, again, explicit formulas. And with this, we can get our explicit formula for I alpha. So I think that's step 7. I alpha, remember, was alpha over gamma of 1 minus alpha. And that equals to, I think, yeah, we just had those two terms. Yeah, so we had this and times this integral plus I times this integral. So really what we're left with is the following. So pi over 2 over sine of pi alpha over 2 plus I pi over 2 over cosine of pi alpha over 2. And it turns out, weirdly, all those terms simplify to something much nicer, because remember, there's this thing called Euler's reflection formula. And you know stuff is serious when Euler comes into play. So, because we know that gamma of alpha times gamma of 1 minus alpha, it's pi over sine of pi alpha. And really witness now beautiful math happening. Because when I first saw this, I was like, okay, you can use it to simplify that, but I was kind of worried because it was just to have a pi alpha over 2. But here we have a pi alpha. Don't worry, just bear with me or fast forward and you'll find a very neat cancellation. Because what do we have then? Because we have this, we can actually solve for gamma alpha. That's just pi over sine of pi alpha times gamma of 1 minus alpha, which is kind of what we have here. And so, what is our integral? Again, just to remind you, I alpha was our exponential integral that will give us our answer. So I alpha then just becomes, where was I? Yes. Sorry about that. So it was alpha over, so 1 over, just to remind you, 1 over gamma of 1 minus alpha. You can just solve then, it becomes gamma alpha over pi sine of pi alpha. So this thing then just becomes alpha over pi gamma alpha sine of pi alpha times this pi over 2 business and then those weird terms that we still don't know what they are, sine of pi alpha over 2 plus I over cosine of pi alpha over 2. Now, the pi's, they cancel out, so that's good. And then what you're left with is alpha, gamma alpha over 2. And again, you should still be worried because here we have kind of the wrong terms. But here's what saves us. Distribute sine of pi alpha everywhere. Over 2 plus, again, sine of pi alpha over cosine of pi alpha over 2. And then I. And here's a cool observation. Pi alpha, it's 2 times pi alpha over 2. And here comes the most beautiful thing of this video. Now we can use the double angle identity for sine. So we get alpha, gamma alpha over 2. 2 sine of pi alpha over 2. Cosine of pi alpha over 2. Over sine of pi alpha over 2. Plus I, 2 sine of pi alpha over 2. Cosine of pi alpha over 2. And again, just math is pretty. That's all I can say. Cosine of pi alpha over 2. All right, and now again, the most beautiful part of today's video. Those things cancel out. Those things cancel out. And what you're left with is alpha, gamma alpha, alpha of cosine of pi alpha over 2 plus I sine of pi alpha over 2. But that is gamma alpha, gamma of alpha, and this is just a complex exponential EI pi alpha over 2. And lastly, well, I don't know why I didn't simplify this before, but one of the nice properties of the gamma function is that it's like a factorial. So alpha gamma alpha is gamma to the alpha plus 1 EI pi alpha over 2. And therefore, I alpha, it's simply, remember, this was this complicated integral that we made even more complicated. It turns out it just simplifies to this. How easy is that? Lastly, of course, we have this, but how does that simplify, or like how does that relate to our previous problem? Well, what do we know? We have integral from 0 to infinity, EI x to the 1 over alpha dx. That was I alpha equals to gamma alpha plus 1 EI pi alpha over 2. And then, if you just take imaginary parts, well, this is real, so we just take the imaginary part of this. We get integral from 0 to infinity, sine of x to the 1 over alpha dx equals gamma of alpha plus 1 sine of pi alpha over 2. And therefore, remember what alpha was? Alpha was 1 over n. So on the one hand, we get integral of sine of x to the n dx equals gamma of 1 over n plus 1. And then this is sine of pi times 1 over n over 2. So pi over 2n. And this is your formula. How nice. And lastly, in case you're skeptical, first of all, as I said, n has to be greater or equal to 2. Otherwise, you would get a wrong identity for sine. But just to double check if it's the same thing with n equals 2 that I did in a previous video, this says that the integral from 0 to infinity of sine of x squared dx it's gamma of, in this case, 1/2 plus 1, so 3/2, sine of pi over 4. And again, by this identity with gamma, this is 1/2, gamma of 1/2. And then pi over 4, it's 1 over root 2. And gamma of 1/2, you can calculate this to be square root of pi. And it basically becomes a Gaussian integral, I think. And 1/2 times square root of 2 is square root of 8. So indeed, we get the same answer that I calculated in another video. And how many contour integrations did we do? 0. So even though we use complex numbers, it was just a really cool, adventure through all the special functions and a bit of analysis too. Alright, so I hope you like this amazing integral. If you want to see more math, please make sure to subscribe to my channel and please click the notification bell. Thank you so much.